Okay, the first problem, what is 4% of 1,100? We want to convert 4% to its decimal. So we're going to remove the percent sign and move the decimal place over 2 places over to the left. So here, 4% is 0.04. Is that correct? Right? So then it says 4% of is always translated multiplication. So I multiply. So here I have 0.04 times 1,100. That on your calculator is 44. D. Okay. If you have questions, just let me know, and we can talk about whatever question that you may have. Number 2, for all x plus 4 times parentheses x minus 5 is equal to, and I think you all got that one, but I'll put it right here. So just a straightforward FOIL, first time the first is x squared, outer times the outer, minus 5x, inner times the inner, plus 4x. Then the last time the last, minus 20. So we get x squared minus x minus 20. Right? So we got G. If x plus y equal to 1 and x minus y equal to 1, then what is y? Now, there's a couple of ways you can work this. X plus y equal to 1. Then here we have x minus y is equal to 1. I use what's called Gaussian elimination. We have 2 equations. We form a system of equations. And you can use substitution if you want. That is, you can take one equation, solve for a variable based on the other, take that information, put that into the second equation, solve for that variable. You can do that, and I will do that one, that method. Let's first do it like this. You choose whatever method that you prefer. In my classes, I have students that come from high school and they say, my teacher taught us this way. Somebody else say, well, we learned it this way. Then my method is way different than theirs. So my thing is, whichever way that you're comfortable with, that you understand it, do that. So here, this is called Gaussian elimination. Some folks just call it the elimination method. So this is very simple. Notice that if I add the corresponding variables, the y would cancel out automatically. X plus x is 2x. Y minus y is 0. That's equal to 1 plus 1. I get 2. I solve for x here. X is equal to 1. But notice the question, what is y? So here, for the first equation, x plus y is equal to 1. If I know that x is equal to 1, I get 1 plus y is equal to 1. Subtract 1 on both sides. Y is equal to 0. Right? Now the second method is called the substitution method. Have you all heard of that before? Have you heard of the elimination method before as well? Okay, so here we can solve by substitution. Substitution method says take one equation, let's say for example the first one, x plus y equal to 1, solve for one of those variables. So if I solve for x here, I get x is equal to 1 minus y. Solve for one of those variables based on the other variable. So I have a variable expression for x. X is equal to 1 minus y. Now the second equation, we have x minus y is equal to 1. Isn't that the second equation? Right? That's the second equation. I'm going to take x equal to 1 minus y and substitute it into the second equation. Replace this x with 1 minus y. So here I have 1 minus y. Just put that in parentheses to denote that it's replacing x. Minus y is equal to 1. Bless you. So this is 1 minus y is equal to 1. This is 1 minus 2y is equal to 1. So subtract 1 on both sides, I get negative 2y is equal to 0. Divide both sides by negative 2, I get y is equal to 0 divided by negative 2. That's just 0, right? And for that problem, you were asked to solve for y. What is y? Y is 0. So if you were asked to get x and y, well, that's no problem. Since I have here that x is equal to 1 minus y, if I was solving for x2, that would be x is equal to 1 minus y. Y is 0. So I get x. My microphone fell. X is equal to 1. But you were asked to solve for that y. Next one. What is the slope of the line passing through the points, the two given points? So we recall that the equation for the slope is that y is equal to y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. Do you remember that? Right? And so here we have x sub 1, y sub 1, x sub 2, y sub 2. So the slope is equal to the y sub 2, which is negative 3, minus y sub 1, which is 7, all over x sub 2, which is 3, minus x sub 1, that's a negative 2. So here we have negative 10 all over 3 plus 2, right? That becomes 3 plus 2. So this is negative 10 all over 5. So the slope is equal to negative 2. Did you get that? Good, good. All righty. If the measure of an angle is 37.5 degrees, what's the measure of its supplement shown in the figure below? Well, the supplementary angle, that result must equal 180. So that's the key that is not given, but we know from geometry. So let's call this x. So we know that x plus 37.5 degrees has to equal 180 degrees. Straight line angle is 180. So subtract both sides by that 37.5 degrees, we get x is equal to, it comes out to be 142.5. Is everybody happy with that? When I was in graduate school working on my master's and going into the PhD program, I had a professor. His name was Dr. Charles G. Cullen. He was a specialist in linear algebra. When I was in college at Alabama State, Dr. Hickman, one of our professors there, asked me where was I going to graduate school, and I told him that I'm going to the University of Pittsburgh. So he gave me a book. Dr. Hickman at Alabama State gave me a textbook. He said, William, he said, when you get there, you may take linear algebra, and your instructor may be Charles G. Cullen. And he gave me a book that was written by Charles G. Cullen. It's an old book, very old. And Dr. Hickman said, Cullen is world-renowned and a leading mathematician in the subject of linear algebra. And you know, time had passed, and one day I was sitting in a linear algebra class in graduate school. And it didn't dawn on me. I'm telling y'all, it didn't. It didn't dawn on me that the professor that I had at the University of Pittsburgh was Dr. Charles G. Cullen. I didn't realize it. Our professor from Alabama gave me this guy's textbook, and the textbook was like, I don't know, like in the 60s or something. It was very old. And this guy, he was pretty old then. This was in the early 90s. And the reason why I thought about him is that he would work a problem and he would ask the class, is that okay, or do you all like that? Well, for me, I didn't really like a whole lot of it because it was somewhat tedious to even try to grasp, the math. The higher you get, it becomes very theoretical. So anyway, what is the sine of angle A in the triangle below? So you have to remember a little bit about trigonometry. Did you all have trigonometry? A little bit? Okay. So you talk about sine, or cosine, or talk about tangent, and then you got secant, cosecant, and cotangent. Let me label what they are for us. And if you will, I'm going to call this side X, call that side over there Y, and then I'm going to call this R. In physics, we call, that's the hypotenuse. We call it R because that's the resultant force angle that's shooting out in space. So that's the resultant. So if you have a triangle, is everything okay? Okay. What's funny? I mean, you all could tell me what's... Oh, okay. Well, if they want to come, do they need this? Or do they need the ACT prep, or are they just waiting for you all? Okay. Well, they're welcome to come if they need this. But, okay. Anyway, so we look at the cosine. This is angle A. So if you want to find the cosine, we'll just call that A. The cosine is always, we call that the adjacent. This is the adjacent side, by the way. And this side is over here is called the opposite. And this is called the resultant, R for the resultant. So cosine is always the adjacent over, we also call that the hypotenuse. We use the phrase hypotenuse. So the cosine is always the adjacent over the hypotenuse. And if you will, I'll just say X over R. Is that okay? It says the same thing, adjacent over the hypotenuse. So X divided by R. And then the sine of angle A is the opposite over the hypotenuse. So that's Y all over R. And then we talk about the tangent of an angle. The tangent of angle A is the opposite over the adjacent, as Y over X. Sine is the opposite over the hypotenuse, Y divided by R. And then you have three more. There are 6 trigonometric forms. So here we have secant of A. The secant is actually 1 over cosine of A. So the secant takes the reciprocal of the cosine. So this is R over X. Cosecant of A is the reciprocal of sine. Everything here in math, and particularly in algebra, and also trigonometry, relates and correlate to opposites. So this is R over Y. And then the cotan of A is 1 over tangent of A. So that's X over Y. So talk about the sine then. Talk about sine of A. So that's going to be the opposite over the hypotenuse. That's going to be 6 over 10. So the sine of A is 6 divided by 10. That's 0.6. You get H. And if they were asking to find the cosine of A, we can list that too. So cosine of A, the cosine is the adjacent over the hypotenuse. So that's going to be 8 over 10. Or 0.8. And then I'll just find one more, the tangent of A. So the tangent is going to be the opposite over the adjacent, 6 divided by 8. 6 divided by 8, or 3/4, or 0.75. And then, for the other three, secant, cosecant, and cotangent, you're just taking the reciprocal of these three guys. So you flip sine, you get the cosecant, you flip the cosine, you get the secant, you flip tangent, you get the cotangent. Now here's something to remember, and it helped me out when I took trigonometry in terms of how to remember the secant, cosecant, and the cotangent. Is I told you the key that everything in math, and particularly with algebra, deals with opposites. Opposite is the key. Opposite is the key. And I told you when we first came here, the purpose of all this was that God made it, right? God made everything. He made the mathematics, right? So he made it. When God made everything, did he put opposites already in nature? Right? Male and female. Whether it's in the human species or with animals, male and female. Right? Opposites. Opposites do attract. Negative and positive. They go together, right? So think about this. When I was studying trig, I used to think that the cosine ought to go with the cosecant because I was just thinking C go with C. C, okay, I'll see right there. And then I would think sine ought to go with the secant. But look, algebra deals with the opposites, right? So here, cosine goes with the secant. It's going to be the opposite. Right? And then the sine, I'm going to pair that with this C, with that cosecant. That's how I remember, those terms. And then tan and cotan, that just rings a bell. Okay. Everything is the opposite. You have an equation, x plus 5 equal to 10. To solve for x, you subtract 5 on both sides because 5 was added to the left side, so you subtract it. That's the opposite, right? If you get 3 times x equal to 12, 3 times x equal to 12, you divide both sides by 3 because 3 is multiplied to x. How do I get x by itself? If it's 3 times x equal to 12, I divide because division becomes the opposite of multiplication. Does that make sense? God designed it like that. All right. So, let's look at the next problem. What is the total cost of 2.5 pounds of bananas at 34 cents per pound? And if I know the weight, the pound, I can take the pound times the amount or the rate, and that'll give me here the cost. And then it says, in 2.5 pounds of tomatoes at 66 cents per pound. So let's see. So that's going to be 2.5 times 0.34. Just put that into an expression, plus the 2.5, which is the pounds of tomatoes, and those tomatoes is 66 cents per pound. And so that gives me, did you work that out on your calculator? What does that give you? You could tell me. Okay. So we get C, 250. Very good. Now, sometimes these problems on these tests, they have a trick to them. You want me to show you the trick for this problem? The trick is this. 2.5 is there, 2.5 is there. They're common. So if they're common, then I can factor out a 2.5 from both of these expressions, and I have here 0.34 plus 0.66. What's 0.34 plus 0.66? 1. Right? So you just get 2.5, $2.50. You can do that when you have a common term that shows up in both places. That's called factoring, and the backward version of that is the distributive property, right? Because if I distribute 2.5 to 0.34, I get 2.5 times 0.34. Distribute the 2.5 to 0.66, I get 2.5 times 0.66. That's the distributive property. Okay. Relationship here between the temperatures in terms of Fahrenheit and Celsius. So here we have the formula that Fahrenheit is 9/5 times C for Celsius equal to 32 degrees. If the temperature is given to be 14 degrees Fahrenheit, can we find the temperature in Celsius? So subtract 32 on both sides, so I get 14 minus 32 is equal to 9/5 times C. Get negative 18 is equal to 9/5 times C. So now I'm going to multiply both sides by the 5, divide both sides by the 9, and so I get negative 18/1, if you will, times 5/9. That's equal to C. 18 divided by 9 is 2. 2 times 5 is 10. Negative 10 is the answer. 18 divided by 9 is 2. Right? Two times 5 is 10, is negative. So I get negative 10 degrees Celsius is what they're looking for. Put a hat on that. Is that okay? As Dr. Cullen, he would say, is that okay? Amy drove the 200 miles to New Orleans at an average speed 10 miles per hour faster than her usual average speed. If she completed the trip in 1 hour less than usual, what is her usual driving speed in miles per hour? This is the kind of problem that you look at it and you say, that's going to take me more time. You mark it, you skip that, go to the next one that you can do. Come back to this, right? So, but since I'm here, I'll go ahead and do it. So let me show you. So we're talking about speed. Talking about speed. So the speed, we call that the rate. So if you talk about a car is traveling 50 miles per hour. So 50 miles, that's the distance per hour divided by time. So rate is equal to distance divided by time. That's the key. So here we have rate is equal to distance divided by time. So if that's the case, then if you think about that, that implies that, just say here, distance, multiply both sides by time, I get the rate times the time is equal to distance. So just say distance here is equal to rate times the time. They went to Jack's and they didn't bring us anything, and I could smell like a hamburger or something with, I don't know, cheese and mustard and ketchup and onions on the sandwich, and it smells pretty good. Is that about right? Yeah. You can't fool that nose right there. Well, thank you all. Well, maybe next time you all will think about us. Us four, we're in here starving. I'm so sorry. I have this one. And this one here is a smaller print. I don't know if you can see that, but next time I know to make 5 copies. So I'm going to say distance. I'm going to call that D. We're not going to write all these words. Distance is equal to R times time. You've seen that before, right? Distance equal to rate times the time. Okay. So we're okay with that. Distance equal to rate times the time. Because the rate is the distance divided by time, so I can multiply both sides by the time, so I get distance is equal to the rate times the time. Very good. You're going to make a chart. It's a very simple chart, and you put everything in the chart, and then once you have that, then you can start working with the items in the chart. So we allow the chart to work for us. I'm going to put everything in this chart. So here's what we're going to do. So I got 3 things. I got distance, I got rate, I got the time. So here, I'm put rate there, time, distance. So it says that here, Amy drove the 200 miles to New Orleans at an average speed 10 miles per hour faster than her usual average speed. So the distance is 200. Tell you what. Let me do this. I just want to show you something. Okay. I'm going to hold that. Distance is 200 miles. We get that. So here, she's driving from wherever she's driving from, she's going to New Orleans. It's 200 miles. So it says here, she's driving at an average speed 10 miles per hour faster than her usual speed. So we're going to say the first one is her usual speed. And then the other one would be her unusual speed. So say for example here, if her speed, her usual speed, let's say is X miles per hour. So now she's going a little bit faster. So this is, we'll just say this is her faster or unusual speed. She's going 10 miles per hour faster. So that's going to be X plus 10. Whatever her speed is, she's going 10 miles per hour faster than that. So here in algebra, you say whatever that is, well, whatever in algebra is X. So whatever, put a quantity there, because mathematics wants to always quantify things. So people like to talk in abstractions. You know, they said. Now, no, mathematicians say, who are they? How many of them are they? Just can say they said. Because people come to me and say, well, you know, they folk talking. Well, who are they? Most times it's like 1 or 2 people. But they say, want to make it seem like it's a lot. Mathematics, you got to quantify what's the number, right? If you don't know the number, put a variable there to represent the number. It says if she completed the trip in 1 hour less than her usual time, so her usual time, I'm going to call that T. Since she's going faster, her time down there is less. So this is going to be T minus 1. Right? So since the rate times the time is equal to the distance, this is x times t. Right? And here, and if you will, I'll put this on the side to think about it. Well, that's equal to 200, by the way, because that's the distance. And then here, this distance is the rate times the time. That's going to be x plus 10 times t minus 1. Okay. So her distance traveling to New Orleans, doesn't matter if in one time she's going faster than the other, that total distance is still 200 miles. Right? So the two distances equal. This is the same over here as well. That's also equal to 200. So here we say since the distance is equal, we have x times t is equal to x plus 10 times t minus 1. Right? The distance set to equal each other. So if that's the case, I solve this. I do the best I can. So this is x times t is equal to the right side. We FOIL that out. First time the first is x times t. Outer times the outer is x times negative 1. That's minus x. Inner times the inner is 10 times t plus 10 times t. And then the outer times the outer, well, the last and the last, excuse me, is negative 10. Now notice here that if I subtract xt on both sides, it cancels out. Well, good for me, because I won't try to get rid of some of this stuff anyway. So I get 0 is equal to negative x plus 10t minus 10. Now, here's what I'm going to do. I want you to see this. See that 10t minus 10? That looks somewhat like t minus 1. I see it in there. But I need to get it by itself, maybe. So look, this negative x, I'm going to add x to both sides. So when I do that, don't you get x is equal to 10t minus 10? Right? I just added x on both sides. Now watch this. Now see here you at a point, and to be honest, you got a point where you're like, what the heck is going on, right? Because no. But I do know that life itself is coming from this chart. Because when Adam and Eve were in the garden, their life came from a source. And so they knew that if they wanted to make it in life, they had to always refer back to the source. The source here is that chart up there. That chart has, see that time is t, and then it also says t minus 1. Well, I'm looking at a t minus 1. If I factor out a 10, it'll be 10 times parentheses t minus 1. Because here's the problem. Here's the problem. I have an equation, but I got two unknowns in it. I cannot solve, I don't care how smart you are, you cannot solve one equation with two unknowns. You want one equation with one unknown, then I can solve that unknown. I have one equation, I have two unknowns. If I had two equations and two unknowns, I can solve that using the elimination method. But this is one equation. I got x depends on 10. X depends on t. What is t? I don't know. Right? So I want to try to connect in some kind of way so that I end up with an equation with one unknown. So I can just either solve for x or just solve for t. So here, I have x is equal to 10 times parentheses t minus 1. Now I go back up here to this table, and I notice here that t minus 1 times, well, let me write it like that. X plus 10 times t minus 1 is equal to 200. I don't want to say it's equal to x times t because x times t just gives me still two unknowns that I'm trying to eliminate to get one unknown. So check this out. This is t minus 1 in there. T minus 1 is equal to 200 divided by x plus 10. I just divided both sides by x plus 10. I get t minus 1 by itself. So t minus 1 is 200 divided by x plus 10. That's what I need. I need t dependent on x. So if that's the case, I come here, I have x is equal to 10 times t minus 1. But t minus 1 is the 200 divided by x plus 10. Okay. All right. So now, if that be the case, I'm going to multiply both sides by that denominator. Multiply 10 times the 200. So here, this is x is equal to 2,000 all over x plus 10. Multiply both sides by x plus 10. I get x times x plus 10 is equal to 2,000 over x plus 10 times x plus 10. So the x plus 10s there cancel out. So now watch this scary thing, but watch what happens. So this is x times x plus 10 is equal to 2,000. Here I have an equation with just one unknown, x. And if that be the case, then I can solve for x. Well, look at this. This is x squared plus 10x equal to 2,000. Subtract 2,000 on both sides. X squared plus 10x minus 2,000 is equal to 0. This is a quadratic equation, right? Where you can solve by the formula, or you might be able to factor. We can factor this. This is x parentheses times some other x over here. What are the factors of 2,000 and such that the sum of those numbers would give us that positive 10? 2,000 is big. You can think about 200. 200 is big. You can think about 20. I like 20 better, right? Take 20, break it down into two numbers. Multiply two numbers, you get 20, such that some kind of combination of those numbers will give you, here in that case, a 1, right? So what are we thinking? Factors of 20 would be what? Four and five, right? 4 and 5. Well, 4 and 5, but here we brought it down. So that's going to, for this problem, that'll be 40 and 50, right? What's 40 times 50? Okay, good. So here, but the sum of the numbers has to give us 10. So that looks like you should have, what, positive 50, negative 40. So plus 50, negative 40. That's equal to 0. So you get x is equal to negative 50. No, x is equal to 40. We're talking about here, x represents what? X represents rate, a speed. So if you're traveling negative 50, you're not doing anything, right? So here, this person is traveling 40 miles per hour. The time is in miles and the units in hours, so this is 40 miles per hour. That's x. The question now, what is her usual driving speed, her usual rate? That's x. That's 40 miles per hour. All right. So the usual here, 40 miles per hour. And then she's going faster, so there she's going 50 miles per hour over there. But they didn't ask for that. They asked for the usual driving time or the driving speed. Right. Very good. Any questions there on that one? Okay. Let's look at the next one. Number 10. A map is laid out in the standard XY coordinate plane. Another phrase for the coordinate plane we talked about when we first got started was the Cartesian product, right? Named after René Descartes. Do you remember that? Remember that? Okay. René Descartes, who said, "Je pense donc je suis. I think, therefore I am." He said, because of my physical existence, it is the case because of what I think, my conscience. That when God made man, the book says that man, he was just a physical quantity. And then God breathed into man, he became a living being, he became a soul. That's what René Descartes was saying with the value for y. Y becomes the soul part, the mind part, and the x becomes the physical quantity. That's what he was talking about here when he drew out this XY plane. Just wasn't talking about math, he was talking about life. So, a map is laid out in the standard XY coordinate plane. How long in units is an airplane's path on a map as the plane flies along a straight line from city A, located at 20, 14, to city B, located at 5, 10. So let's see if we can put that on the grid. Let's say 5, 10, 15, 20. Say 5 units there. 10. Say 15 there. So now let's see if we can label these points. So 20, 14, go over on the x 20, go up. Oh, that's 15. I meant to put a 15 there. 15. Okay, it's getting kind of. Is it getting hot in here to you all? Just me. I'm the only one working, right? Okay. That's why I'm getting hot. Okay. Drink some juice. This juice is not good for you. Too much sugar in it. I went to Best Wings in Huntsville on corner of Maskin Lake and I think Blue Springs Road. They got some really good wings. They got some juice there that's really good juice. So I drink like maybe 5 sips of it each day because too much of it is not good. It's not good. Okay, anyway. You don't believe me, do you? I had a friend when I was growing up, he'd always say something stupid like that. And he'd say, "You don't believe me, do you?" And I said, "No, I don't believe you." Okay, and next time our friends are going to bring us Jacks. Right? Okay, I'm just joking. Chicken would be good. Okay, they're passing out gum. Rah, you want some? Reddy, I'm sorry, you want some gum? So, no, I'm fine. Grandmama told me I can't chew gum in public like that, you know, especially at church or anywhere. I used to get in trouble, so it just stuck with me. So when I'm in the car by myself, I chew gum real quick and then I spit it out. I just want the sugar and then I'm done. My middle son, he's on the autism spectrum and that's what he does. He can go through a pack of gum in one day and I can too. We get him the sugar free, you know. You get the sweetness out of it, he throws it away. Okay, so here, the first point is 2014. Sounds like a year. So it's about right there. That's point A. Then the second point is 5, 10, 15, 20, 25, 30. That's point B. Okay. The red is too bright. So here's the path of this plane. It's a straight line. Well, my line is not too straight, but anyway, you get the point. We need to calculate here the distance from A to B. To do that, I want you to see the triangle. Do you see the triangle? There's a triangle there. Do you see it? Okay. And you've got to be careful. It's right there in your face. It may knock you down. Okay. See if I can blow it up. You don't see it. It's a right triangle. So the distance becomes the hypotenuse, right? So now I need the change in the y, that is the change in the y here, and also over here, delta, the change of x. So the change in y, well, it goes, if we put the point there, this was 20, 14, and then b was 5, 10. So the change in the y values would be the 14 minus 10. 14 minus 10, or just 4. The change in x values would be the 20 minus the 5. 20 minus the 5, or 15. Okay. So I'm going to call this side D for distance. I'm not that smart. It just makes sense. Okay, D for distance. So, where'd you come up with that from? D for distance, period, right? Okay. So I'm looking for the distance, but the distance is the hypotenuse. Oh, do we recall the Pythagoras Theorem? Do we recall that? The Pythagorean Theorem, the Theorem of Pythagoras is how it was stated in the Greek. So, and here's what's crazy about that, and just say that real quick and I move on. You know, it's not good when you know a lot of stuff about something and you can just talk about it. The Pythagoras Theorem says this, just a little short version, x squared plus y squared, just say, equal to z squared. That's the Pythagoras Theorem, right? The Pythagoras Theorem is only case number 2 of a very large theorem that existed in what we call number theory. It's a very large theorem that they were actually trying to prove, that they couldn't prove. And case number 1 was that the exponents is equal to 1. So if the exponent is equal to 1, you get x plus y equal to z. You find those values. And then case number 2, the exponent is equal to 2. Case number 3, exponent is equal to 3. You get this quadratic cubic form. The next part was the exponent equals to 4, 5, on to n, on to infinity. You got to prove it for all that. So the bigger theory in number theory was that x to the n plus y to the n is equal to z to the n. Can you show this? Can we find values x, y, and z for any n that's in the number system? Well, that was difficult. So Pythagoras, he was strange. He was a strange guy. He did stuff that he wasn't supposed to do. And he had a group of people that met with him. They had like this math circle, which was like a fraternity for those guys, you know, in Greece. You know, you think about that now, it sounds kind of strange. A fraternity based around numbers. What they did, they had this. It was called the Pythagorean group, and he was trying to prove this theorem, and he got to case number 2, And that's what he proved. He couldn't go any further. He said the case number 2 is let n equal to 2. You get this guy. You get these squares. N equal to 3, you get these cubes. N equal to 4, you build all these very funny, nice polygons. And keep on going. The theorem was being proved by several mathematicians of old, all of the great mathematicians. Leonardo, Euler, Descartes tried to prove it. Cauchy, Augustin Cauchy. There was one gentleman by the name of Fermat, F-E-R-M-E-T. He was a French mathematician. He was proven, and I think they said he was maybe on the train or something. He was traveling about maybe a horse and buggy, however they traveled back in the 1700s. They didn't have trains back in the 1700s, so I guess it was on horse and buggy. And he wrote, as he was traveling, that he wrote to Blaise Pascal. Have you heard of Blaise Pascal before? Blaise Pascal. Blaise Pascal gave us a big chunk of mathematics today. And also, the interesting concept of computer science is based on theories of Blaise Pascal. He was writing Blaise Pascal. He said, look, he said, I could prove this guy for you, but he said that my margin is not big enough for me to keep writing. And so he said, if I had a bigger margin, I could actually finish the proof. Well, he died right after that, and so he never could prove it. And that's been called Fermat's last theorem. Well, it was actually proved a few years ago using computers because it was very difficult. But anyway, the subcase of that is called the Pythagoras Theorem. So you think, when you're in school like this, you think the Pythagoras Theorem is pretty neat and, difficult and challenging. And then really it's very easy. It's a very simple case to a very larger system. Anyway. So, using that, so I have here this change in x squared plus the change in y squared is equal to that d squared. And if you just want to write it as x squared plus y squared equal to d squared, that's fine. That's the Pythagorean theorem, right? So that's the theorem of Pythagoras, and we're all familiar with that, right? So we're okay with that. So now x here is the 15 squared plus y is the 4 squared is equal to the d squared, right? So d becomes what? Not the actual number, but tell me what it's supposed to be written as. D is, if I got d squared is equal to 15 squared plus 4 squared, so d by itself is equal to what? Huh? Okay, yes, ma'am, we know that. But oh, you're so smart, damn. What did I tell you Donald Trump said? What did he say? Was it fake news? Yeah. You got to see that when y'all get home. Watch the news. I'm sure they're going to play it. Donald Trump, he's calling out a reporter, and he's saying to this reporter, fake news, fake news. I don't know if you saw that, but it's hilarious. But anyway, if I'm looking for the distance, what's the distance equal to if I know that 15 squared plus 4 squared is equal to d squared? D is equal to what? Square root, right? Are you with me? D by itself is the square root of the 15 squared plus the 4 squared, which the 15 squared plus the 4 squared is 241. So this is the square root of 241. So in other words, here you would have gotten d squared is equal to 241. take the square root of both sides, right, to get D. The square root of D squared is equal to the square root of 241. The square root of D squared is equal to D, right? You get the square root of 241. Are you with me? Does that make sense? Okay. So the next one, a person 2 meters tall casts a shadow 3 meters long. At the same time, a telephone pole casts a shadow 12 meters long. How many meters tall, get out the way, how many meters tall is the pole? Here, I'm comparing something to something else. So if you got a person that casts a shadow, then if you think about it, this person, the shadow, forms a triangle. Then if you have a pole that's so tall, it casts a shadow, it's also representing a triangle, a right triangle, person standing upright, and the pole is measured to be upright. So if that be the case, I can compare two triangles. So we use ratios, right? So we solve this problem. It's the right pen. By comparing two, what we call here, similar triangles. All right? Let's look. I have this person. He's standing up so tall, he has a shadow. This person is 2 meters tall, it says. So I'm just going to write 2 there. His shadow is 3 meters tall. It's a right triangle. And then you have a pole that's even taller. It also casts a shadow. So the person is 12 meters tall. This is how many meters, I'm sorry, the shadow, got to read that better. A telephone pole casts a shadow 12 meters long. So that goes over here. It says here, H for the height. It says how many meters tall is the pole. Do you see that? Can you solve that now? By the ratio and proportion. You remember that? If you think about it, 2 over 3 is equal to H over 12. 2 over 3 is equal to H over 12. You see that proportion? See, this 2 meters on this side, it represents the same side as this height of the pole. And the shadow for the person, 3 meters, also represents, this same dimension for the 12 meters of the shadow of the pole. So I relate them. 2 is related to H. 3 is related to 12. You have a ratio, right? 2 goes to H, 3 goes to 12. So cross multiply, 2 times 12 is equal to 3 times H. 24 divided by 3 is equal to H. So we get here 8, I think it's in terms of meters. That's part C. Is that okay? Any questions? Please do. Feel free. Ask. The Bible says we have not because we ask not. Isn't that what the Bible says? Okay, good. And I'm asking you all for jacks next time because y'all have, I'm just joking. Okay, this problem here. Number 12, a hiking path on the top of a mountain makes at the steepest place an angle of 20 degrees with the horizontal. And they place that right there for us. And it maintains this constant slope for 500 meters. That's the hypotenuse, right? 500 meters as illustrated. Which of the following is the closest approximation to the change in elevation? That is, I want to solve for this side over here, right, in meters over this 500 meter section. So you remember back when I labeled the triangle for those trig functions, and we said that one side is called the adjacent, one side is called the opposite, one side is called the hypotenuse. So this side down here, this is the what? I'm talking to you. What is this side here called? Compared to this angle 20 degrees, this is the what? You wasn't listening. You know, I tell my college students that when I was in high school, well, middle school, our teacher, Herman Watts, probably shouldn't be saying his name because we're going to put this on YouTube, was a good man. We move on. He used to whip us. That's what I'm trying to say. If you couldn't get what you're supposed to get. This is 8th, 9th grade, and he had this big paddle, and he'll put it on you. And let me tell you, after that, you listen attentively. Okay, you listen really good, because those licks hurt. And he was a pretty tough guy. Good guy, very smart, but he got my attention. Okay, we said that for the trig functions, looking at a triangle, I want to label the three sides as either the adjacent side, the opposite, and the hypotenuse. My question down here, what's this side compared to 20 degrees? This is the what? Adjacent. It's the adjacent leg to the angle, right? And so this has to be what? Opposite. It's the opposite side with respect to the angle, right? And that's the resultant, or where the force is being shot out there. That's called the hypotenuse, right? So good. So this is, yes, this is the adjacent side, and this is the opposite. Now, I want to call that, if you will, just for simplicity, let's just call it y. Okay. I want to solve for y using one of those trig forms. I got sine, cosine, tangent. That's all you need. The other three, secant, cosecant, and cotangent, they're just the reciprocal of those guys. So the main three we need, cosine, sine, or tangent. Use here to get that opposite side over there. You know, it's like when the instructor, he asks a question, he's expecting, like, on this side, an answer. You know, see, somebody say something, right? So, now to answer that question, you need to know sine of angle 20 is equal to what form? Cosine of angle 20 is equal to what form? Tangent of angle 20 is equal to what? What ratio? Something over what? And then you think about that, and so you put them together. The sum trig of 20 degrees is equal to something using that side over there. And would I use the adjacent side? Would I use the adjacent to solve for this guy over here? Or would I use 500? Use 500, right? Because this is something that's known, right? Do you know the adjacent side? No. Do I know the opposite? No, but I'm solving for that, right? So what's the trig form that relates the opposite in the hypotenuse? Which one was that? I got to sit down. I'm hearing a lot of fake news today. Fake news. You got to see Donald Trump. He was calling the reporter fake news. You don't say that, man. You're supposed to be the president in a few days. And the reporter's talking fake news. This guy's asking a question. He don't want to hear it. He's saying to the guy, Fake news. That's hilarious. So you gave me some fake news. Because the cosine deals with the adjacent. You remember that? The cosine is the adjacent of the hypotenuse. The adjacent, you don't care for this problem. What am I solving for? The opposite. So which of those three trig forms would use the opposite in the hypotenuse? Okay. I would stay there, but we got 15 minutes to do 7 more problems. It's the sine, right? Isn't the sine the opposite over the hypotenuse? You all don't like me anymore. You don't like me. You don't. Sine of 20 degrees. Sine of 20 degrees is equal to the opposite. Remember we talked about that? Didn't you write it down? I gave it to you. Those who were here, right, in the beginning. It's the opposite over the hypotenuse. Here the opposite is what I'm solving. That's y. That's over the hypotenuse. The hypotenuse is 500. And they give me here that sine of 20 degrees is approximately 0.34. So 0.34 is equal to y over 500. Multiply both sides by 500. So I get 500 times 0.34 is equal to y. And that's a y there. Looks funny. Okay. And on your calculator, decorator. So y is equal to 170. Is that one of the answers? Any questions? This one right here, number 13, let's omit that. My explanation of that, I think it'll take you really high, and it's crazy stuff. Matter of fact, I can explain it. Here's my point of my philosophy. I can explain this problem, you probably wouldn't get it. And so I can explain it, you're like, huh? And then if you see this problem again or something very similar to that, it'll mix you up. I don't know why, but every now and then they will throw, this problem comes from what we call combinatorics. It's a field in mathematics called combinatorics. And in the process of that, it's, let's see. That's number 13. The answer for that is 9, but it's okay. Right? I wouldn't even waste your time trying to explain. If you take your calculator and if you type in the number 5 and put like raised to the 20th power, your calculator will freeze up. It's not going to give you that number. So now you take the number 537, raise that to the 102nd power. 20, 30 years ago, the calculators and the computers, they would crash trying to crunch big numbers like that. There's a pattern that's behind that where we go through and show you the pattern. And I took the ACT when I was in high school. I made, close to 30 on that. And I guarantee you, I missed the problem. And a stupid problem like that I'm not going to waste my time, because you get trapped on one problem. That problem takes a long time to try to solve that guy. You get trapped on that. You wasted 5, 6, 7 minutes where you could have worked some problems that you can actually do. Get those problems right over there. It boosts up your score. A lot of people do poorly on the ACT because they didn't finish it. So the key here is you work through the problems that you can work through. The ones you can't work, you circle those. Then you go back to the ones you can't work, then you try to work those. The ones that are those you can't work, if you got an idea about how to solve them, try that. And then you have a subset now left of the problems that you just have no clue. Guess on those guys. Keep moving. But put an answer for every last one of them. But the ones that you can do those. Ones that you're sure of, I get these right. But make sure you look at all 60 problems. There's 60 problems on this ACT test for the math part. Look at all 60 of them. Which of those 60 that you can do what you can do. The ones you can't do, go back, spend some more time on those. And the ones that you really have no absolute idea about what's going on, hopefully there's no more than about 5, 7, 8 problems. Try to guess on those. Okay? Put something there. Now this problem here is good. If A is less than -1, which simply means that A is a fraction and it's negative. Well, I'm sorry. A may not be a fraction. I'm thinking A between 0 and 1. I took a class and that the only numbers you dealt with were all the numbers between 0 and 1. That's what that class was all about. Just going to investigate the numbers between 0 and 1. That's all. You know how many numbers there are between 0 and 1? It's infinite. It take forever to look at every last one of them. Infinite between 0 and 1. It's infinite many numbers. Wow. It blows your mind. And so we studied men like Cantor and Abel and Dedekind. And Dedekind said, look, you can take the numbers between 0 and 1 and you can slice it in half. And he said, take that half, slice it in half. Take that half, slice it in half. He said, keep on traveling, keep on doing that. Cut that piece in half. That piece that you cut that in half. You know how many times you do that? Infinitely many slices. Boy, it's crazy stuff. Anyway, A is less than -1. Which of the following best describes a general relationship between A to the third and A squared? Here's the key to this problem. The key is this. If A is negative, watch this, A squared is positive. You get that? Take a negative number, square it, you get a positive number. If A is negative, its cube is also negative. So A cubed is less than A squared. Answer. Did you get that? If A is negative, right, let's say A is equal to -5. When you square -5, you get positive 25. If you take -5 to the third power, that's like a negative, right? -125, whatever. Anyway, a negative number is always less than a positive number. So A squared is greater than A cubed. A squared, read that from right to left. A squared is greater than A cubed. If 4/5 to the n is equal to the square root of 5/4 to the third, what is n? Okay, no problem. This is 4/5 raised to the nth power. Now this is 5/4. This is raised to the third power, but the square root is the 1/2 power, right? Square root means the power is 1/2. You say the square root of 6, you're actually saying 6 to the 1/2 power. Right? When you say 16 or the square root of 16, you're saying 16 to the 1/2 power. So you say 16 is 4 to be squared, raised to the 1/2 power. If you have a power raised to a power, you multiply the powers. So you get 4 to the 2 times 1/2, a power raised to the power, multiply the powers. 2 times 1/2 is 1. That's why the square root of 16 is equal to 4. Because it's all in the power. The power is a ratio. It's a fraction. So here, this 5/4, this is raised to the 3/2 power. Where that 1/2 come from? It came from that square root, right? The square root is 1/2. So 1/2 times 3 is 3/2. Now, I got 4/5 raised to the n is equal to 5/4 to the 3/2 power. I can equate the exponents, this n and this 3/2, if the bases are the same. My bases are not all the same. This is 4/5, this is 5/4. But I can make this 5/4 into a 4/5 by doing a flip. If I flip it, that means that I have to negate the exponent. So 5/4 raised to the negative first power becomes 4 over 5. Look at this. So this is 4 over 5 to the nth power is equal to 4 over 5 to the negative first power, and that's all raised to the 3/2 power. See, 4 over 5, if I take its negative exponent, -1, then that simply, it flips the ratio. No? Okay. We actually call this the property of exponents. Right? The first one says that x to the a times x to the b is equal to what? X to the a plus b, right? If I had 3 to the second times 3 to the fourth, you write that as 3 to the 6th power. The second one says that if I have x to the n divided by y to the let's write it like this. Divided by x to the m. They have the same basis, so this is x to the n minus m. Have you seen this before? It's the laws of exponents. The third one says that if I have x times y raised to the nth power, I raise each term inside to the nth power. Number 4 says that if I have x raised to the nth power, and that's raised to the mth power, I multiply the powers. This becomes x to the n times m. Number 5, x to the negative n is equal to 1 over x. You flip it to the n. That's what we're doing here. Number 6, if I have x over y to the negative nth power, this becomes y over x to the nth power. If the exponent here is negative, right, I can make it positive by flipping the ratio. Flip it. Example, take the number 1/2. Right? 1/2 is the same thing as saying 2 to the negative first power. Based on this number 5, right? 2 to the negative 1 is 1 over 2 raised to the first power. So here, number 6 is what I'm using to simplify this problem for me. I'm trying to get the same basis. If I have the same basis, then I can somehow equate the exponents. Well, 4 over 5 does not equal to 5 over 4, but 4 over 5 equals to 4 over 5. So this over here, this 5 over 4 becomes 4 over 5 raised to the negative first power. So this is now 4 over 5 raised to the n is equal to 4 over 5 raised to the negative 3/2 power. They have the same base, so I can set the exponents equal. That is, n has to equal to negative 3 over 2. If the bases are the same, I can equate the exponents. If the bases are the same, what's up top must be the same. Okay. Quickly, let's look at this one. in the standard XY coordinate plane. This is another problem that is tricky and challenging, but I will go over this one. In the standard XY coordinate plane, the triangle with vertices 0, 0, 0, 6, well K, and 2, M, where M is the constant, changes shape as K changes. What are they talking about? Right? So here's what you want to do. Draw out what they're saying to the best of your ability. Just draw it out. You have the X and the Y axis. So here they have the vertices 0, 0. So I put that there. Then they say 0, K. I don't know where that is, but I do know it's on the Y axis because X equal to 0. I'm going to put it here. I'm going to call that 0, K. And then it says 2, M is the other point, the third point. So I'm going to come out here 2 units. Right, for X, and then M, here they say is some fixed number. So this is 2, M. Then they say now form the triangle. So the triangle here is there, goes there, and it's there. Now in black, I'm going to draw the height of that triangle. So the height here is 2. So the area so far is going to be the base. Now this base has distance of K, right? This is K. This whole side is 0, K. This point right here is K. So this is, the area is 1/2 times the base times the height. So 1/2 times the base. The base is K. Here times the height. What's the height equal to? If K here is the base, right? If this is the base, then what's the height of this triangle? Did you say 2? Yes, 2. So the area is equal to K. Now check this out. What if I change it? It says that you can change it. Why can you change it? You can change it because K can be any number on the Y-axis. So I'm going to change it. Right. I have this fixed point at the origin. You got that, 0, 0. That doesn't change. But what if K is down here? It could be, right? Doesn't matter. What it says that 2, M is fixed, so that guy is still up here. Right? So the triangle then is here, there, and there. Okay? Very good. So we do a dot, dot, dot. That's still the height. Right? So the height. Ooh, red doesn't look good. Red, red. Okay, so here, the height is still 2. The base is still K. So this area is 1/2 times the base is K, times the height, that's 2. Still get K, right? So depending on the value of K, if K is small, the area is small. If K is big, then the area is big, right? Look at the answers. The area increases as K increases. That makes sense. The area decreases as K increases. It's not a fraction, right? The area always equals 2. No, the area always equals to K. But that's not one of the answers, right? The area always equals to M. No. The area always equals 2M. No. The area equals to K. So the only one that makes sense is that the area increases as K increases. Do you see that? Whatever the value of K is, look, here's the value of K. If K is small, then obviously since K is the area, then the area is going to be small, right? If K is big, then the area is going to be big because the area is equal to K. So as K increases, the area increases. As K decreases, the area decreases. Okay, gotta move on. Gotta go to Jackson because friends went to Jackson. They didn't bring us anything. What we gonna do, rah? I'm sorry, Reddy. Man, I tell you, I know your whole family, man. What we gonna do, Reddy? Okay. All right, let's do this one. Just give me a couple more minutes and we're gonna go. I know I'm over the time, but I'd like to get these out of the way. In the figure below, AB is equal to AC, and BC is 10 units long. So here you have, this is 10 units, this is 10 units. Now it says BC is 10, right? But if all sides are 10, what do you call that triangle? If all sides are the same, it's called a what? Equilateral, very good. So if it's an equilateral triangle, and since this is a right angle, they're bisecting angle A into half. So this is 5 over here, and that's 5 over there. If I take one of those triangles, look at this one over here, don't you see the hypotenuse or the Pythagoras Theorem? That here, if I solve, I have 5 squared plus h squared is equal to 10 squared. So the question is, what is the area in square inches of the triangle A, B, and C? The area is going to equal to this. The area is going to be 1/2 times the base. I know what the base is, that's 10, right? Times the height, that's that h over there. So the area is going to equal to 5 times h. So let's solve for h over here. This is 25 plus h squared is equal to 100. Subtract 25 on both sides, I get h squared is equal to 75. So what's h equal to? What's h equal to? I don't need to have the calculation, but h is equal to, just simplifying that, just using square roots or whatever, h is equal to what? Okay, I'm Pat Sajak. I'm Pat Say Black. If h squared is equal to 75, h is equal to now how do I go from h squared to h? What did I do? Okay, so if I take the square root over there, I must do what to this side? So h is equal to what? The square root of 75. Thank you. Right? I tell you, you're like, this guy, what's wrong with this guy, man? You know? Y'all make my job hard, man. Ready? What are we going to do, man? So h is equal to the square root of 75. Now, I can break 75 down because that's 25 times 3, right? So what's the square root of 25? 5. So h is equal to 5 times the square root of 3. Does that make sense? So the area, I already got my formula up here, is 5 times h. So that's 5 times, here h is 5 times the square root of 3. So that's 25 times the square root of 3. Look at those answers. The answer is not there, so cannot be determined from the given information. See that? Because we calculate the answer is 25 times the square root of 3. A bag of pennies could be divided among 6 children, or 7 children, or 8 children, with each getting the same number and with 1 penny left over in each case. what is the smallest number of pennies that could be in the bag? Now this is also one of those tricky, problems that you scratch your head on. There's a trick to it. The trick is this. All they're asking for is to find the least common multiple, then it says plus 1. Right? It says with each getting the same number and with 1 penny left over, right? So find the least common multiple, add 1 to it, you get the answer. Can you do that real quick? So here the answer is the least common multiple plus 1. Least common multiple, the same thing as the least common denominator if you had numbers in your denominators, right? So what are the numbers we're dealing with? 7, 6, and 8. So how do we find the least common multiple? I list 7, I list out its factors, well, it's just 7. Take 6, list out its factors, so that's 2 times 3. I take 8, I list its factors, or its prime numbers, if you will. So here, this is 2 times 2 times 2. So the least common multiple, if a number going up and down, if a number is by itself, I bring it down, right? 7. If I have the same numbers up under each other, I just bring one of those as common. So I bring that 2 down, bring the 3 down. These guys are by themselves out there. I bring them down. So here, I get 14 times, here this is 4 times 3, or 12. So that's 168. Is that right? So here, they said you want one penny left over. So that's going to be 168 plus 1. That's 169. Okay? Did you get that already? Bless your heart. You smart. You smart. Okay, 2 more and then we're done. Again, number 19 is a somewhat of a challenging problem. You got to know something in terms of what they're talking about. Now here's what trips me out. Here's the behind the scenes behind this problem. You need to know probability. Did you all talk about probability in school? A little bit about that? Well, good. Because when I was in high school, I don't know if we did or not. I probably missed that problem on the ACT too, because I don't think we talked about probability when I was in high school. Now, we could have, like I told you, the ones who came here earlier, my mind drifted when I was in school, but it's okay. I got it. There are n students in a class. If among those students, p% play at least one musical instrument, which of the following general expressions represent the number of students who play no musical instrument? So if P represents that which is the positive thing that is being sought after, then we say the complement in probability, the complement represents the not. Right? So in other words, if you say that you got out of 100%, if you got 13% made an A, right? So that means that 87% didn't make an A. You got 100 minus the 13, and they gave you the 87%. So we call that the complement. Take the complement plus this positive part, I get the whole. 13 plus the 87 gives me 100. Right? So here, there are n students in a class. If among those students, p% play at least one musical instrument, which of the following general expressions represent the number of students who play no musical instrument? So if p% plays at least one musical instrument, then the complement of that times the number of students in that class would give me those who play no musical instrument. Let me write that out for you. So here, if, I don't like that color. If p% plays at least one musical instrument, then what's this here? 1 minus 0.0p percent plays no musical instrument. And I'll show you how we get the 1 minus the 0.0p, plays no musical instrument. Percents are said to come from the probability. The probability is always a number between 0 and 1. So if I have the percent, 13% is actually for probability is 0.13 for the probability. Right? So you get the percent from what was initial, that was the probability, the percent, the decimal. The decimal is always between 0 and 1. You can make that decimal or percent by multiplying it by 100%. So you get 0.13, right, times 100%, you get 13%. So when they say p percent is translated, it's translated 0.0p for the actual number. Right? So here, what I have then is those who don't play any musical instrument becomes the 1 minus 0.0p in parentheses times n, but then I want to get the number. I don't want to get the decimal. So to get the number, I'm going to multiply and divide by 100%. That gives me the number. Let's see. So thus, the number that plays no musical instrument is this, is 100% divided by 100. Here this is times 1 minus 0.0p times n. N is the total number. N is the total number of students. The total number of students times this percent gives me the number of students that I'm looking for. So percent divided by percent, if you will, those percent signs cancel out. So what I have is, I have 100 times 1 minus 0.0p times n all over 100. Don't cancel out the 100 because you'll miss the answer. Multiply 100, distribute that through the parentheses, and that gives you 100 minus, what's 100 times 0.0p? Move the decimal place over 2 places over to the right. That just gives me p, right? Times n all over 100. That's C. And the last one. And the last one, I've been working all night. I want you to figure this one out, and then we're going to go. So this is going to be based on you, based on your time. If you can get this problem right, we're leaving. If you stay here all night, because I'm not going to let you go. I'm just joking. I want to go too. But see if you can get this. I'm going to read this. Okay, starting at, this is good. Like I told you in the beginning, those who came in the beginning, look, mathematics, thinking, right? Well, think a little bit. And I gave you all those little drill problems that had you all to think a little bit. So starting at her doorstep, Ramona walked down the sidewalk at 1.5 feet per second. That's her rate, that's her speed. And she does that for 4 seconds. Then she stopped for 4 seconds, realizing that she had forgotten something. So for 4 seconds, she's just standing right there in one spot. Next, she returned to her doorstep along the same route at 1.5 feet per second. So now she walks for 4 seconds, then she stops for 4 seconds, and then she realizes she forgot something, and so then she walks back home, right, at the same rate, 1.5 feet per second. The graph of Ramona's distance, d, from her doorstep as a function of time t would most resemble which of the following? What do you all say? What say ye? And then, of course, we talk about it. Boy, it gets real quiet. Anyone? Mm-hmm. Okay. Let me see if I can help you out. You see this t-axis? That's the time, right? Then up above is the d, that's the distance, right? So here's what that means. As time is going along on like the x-axis, the t-axis, as time goes, is there movement? Is the distance, is she going somewhere? Right? So here it says yes, she is. And then notice this guy says that she's traveling, she's moving as time goes, she's always moving. But this problem says she stopped for 4 seconds. So if she stopped for 4 seconds, that means the time is still going for 4 seconds, but she ain't going nowhere. Right? Does that say it? Look at G. Now we're going to rule out F, right? Because here it doesn't show where she stopped. It doesn't even show where she went backwards. G says, look, she's moving a distance, but then she goes back and she's returning. She's still traveling with time, but she's going back in the opposite direction. That's what G says. G doesn't say anywhere where she stopped for 4 seconds. You see that? Doesn't show that. H, let me move down. Is it H? Why wouldn't it be H? It does. It does. But here, this says that, okay, she's traveling for 4 seconds. She stops. Time still goes on when you stop. Even though you stop, isn't time still moving? Time always moves, right? But she's not moving anywhere. That's the distance, right? She's not moving anywhere. But then it says after 4 seconds, here, she's going on somewhere else. She ain't going back home. Because that says that the distance is increasing, right? So, J, you got it. Okay, let's go home. Very good, very good. Let me close this out.